So welcome back. Today we'll be introducing a quantity called as density operator. So let us start this discussion. Introduction to density operator. So this makes our life easier, much easier when we actually have to carry out a measurement and we have an operator and we want to measure its expectation value. In that case, density operator becomes very handy. So let us see. So let us first consider a superposition state, which is psi. So this is a superposition state which can be expressed in terms of linear combination of eigenstates, right? So you can have summation over all n Cn, and these are the eigenstates, and these are also stationary states. So any time dependence that goes in, because psi is time dependent, so Cn will have time dependence, or the coefficients of this linear combination will have time dependence part, right? Okay, so this is like if for a two spin system, if you want to consider this, psi will be equal to C alpha alpha plus C beta beta. Okay, this is just a just an example, uh, and in general we can write the same equation as psi is equal to summation Cnn over all n's, right? Okay, so now to understand how to actually estimate the time dependence part, see, when you're trying to identify a system, or when we are trying to find out energy of a state, we need to first set up the Hamiltonian, and then we also need to set up the uh, spin state, right? So if we know both, in certain cases we should be able to estimate the energy of the particle. So if we do not know state, we can't actually apply Hamilton. We don't know on how do we have to apply Hamiltonian, or on what state we have to apply Hamiltonian to. And to understand the state, any given quantum state, we need to know the eigenstates and the coefficients. So let us now try to see how to get these coefficients. So for that, let us consider a state m, a general state m, and try to take its integral with respect to psi. Okay, so this is a general state. Any general quantum mechanical state defined by m. Okay, now this can be written as, if you see here, so psi can be picked up from here, and what you will have is summation over all n bra m Cn and ket n, right? Now since all these states are orthonormal, now let me first expand this. So if, because this is summation over all n, so this will vary. So you will have m c, let's say c1 1 plus m c2 2 plus so on, right? So now all these states, state 1, state 2, state 3, up state m and state n, all these states are orthonormal, and only when m is equal to n, the integral will be non-zero, right? In all other cases, because these are orthogonal, so integral will go to 0, and thus we can write the above equation as, so substitute m equal to n, so you will get n psi is equal to n Cn this is n summation over n, and this quantity will go to 1 because again this is integral between with n with respect to n, and because these are normalized, so all of this will go to 1, so you are left with only Cn, right? Okay, so this is an important identity, that n psi is equal to Cn. So you can find out the coefficient Cn if you take integral of eigenstate with respect to a superposition state. Okay, now psi is equal to summation Cn n summation over all n. Okay, now you substitute the value of Cn from here into this equation which we started with. So what you will get is summation over all n, and I have n psi, and then I have ket n, right? So I've substituted the value of Cn from here. Okay, now this is a number, and thus it can be moved here, so I can very well write it as summation n ket n bra n psi ket psi, right? Now if you see that both sides you have ket psi common, so that means this whole quantity will be equal to 1, right? Or we can say unitary operator or unity operator. So then we can say summation n is equal to E n cross n, right? Okay, so this is an important identity which we'll be using later. Okay, so let us make a note of this. Now let's consider a case of spin half system. Okay, so for spin half system, the superposition state will be, as I said earlier, C alpha alpha plus C beta beta. Now since psi is normalized, we take it as normalized, so that would mean that if I take bra psi and ket psi integral, this will be equal to 1, right? Okay, that means if I take the right hand side will become, if I take bra psi and ket psi together, so that would mean that I have alpha C alpha star C alpha alpha. So this term comes when you take the bra of the whole thing, so this will become bra and this will become C alpha star. That's how it will come here, plus you will have alpha C alpha star C beta and beta plus beta C beta star C alpha alpha plus beta C beta star C beta beta equal to 1, because this is equal to 1, so this whole thing will become equal to 1. Okay, now that means this implies that C alpha star C alpha plus C beta star C beta equal to 1. So this comes from the fact that two of the integrals which will have alpha and beta terms So this will go to 0 because this is integration between two orthonormal states, and similarly this will also go to 0. So only this will survive. So alpha into alpha will go to 1, beta into beta will go to 1. So these two will survive, and you are left with C alpha star and C beta star, right? So that is very simple to see. Now this is nothing but probability of finding the spin in beta state, right? Okay, so now let us try to measure an expectation value, which is the average over all measurements or over many measurements for a given operator A. Okay, so for a given operator A, expectation value is shown with two curly brackets like this, and what you will have here is psi A psi. So of course I'm imagining that psi is normalized here, normalized. Otherwise I will have a denominator also containing the denominator will be psi psi, right? But because this is equal to 1, so I'm not writing it over here. Okay, so I'm omitting the denominator part. Okay, so now let us expand this. Okay, so for any when psi when ket psi is expanded, so this will be expanded with respect to the coefficient n, and when bra psi is expanded, this will be expanded with respect to coefficient m. Okay, and since summation is taken, so it really does not matter, but this is just to keep the distinction between bra and ket. Okay, so what we'll be doing is, so we will write this as summation m cm star, because this is bra over here, and then you have m operator A summation n cn ket n. So all I have done is I have replaced psi with summation n cn. So superposition state is expanded into the eigenstate. So linear combination of eigenstates. That's all I have done. Okay. So now I can take the summations out. So I will have double summation m summation n, and I'm left with cm star. These are numbers, so I can take them out, and I'm left with m a n, right? So this is nothing but matrix element of operator A. So remember that operators can be written in matrix representation, and this is mth row and nth column matrix element of A operator, right? So if you remember that we had for spin half system we had so for spin half system we have two states, alpha and beta, and in the alpha beta eigenstates, alpha can be written as in matrix form as 1 0, and beta can be written as 0 1. These are the two column matrices, and we had also written, if you remember, the matrices for iz operator, I plus step up operator, step down operator, and ix, iy, etc. Right? We had written matrix representation for all of this. Now let us see how to find the cm star. And so this matrix we can write. If we can write the matrix, we can identify the matrix element. Now the job is to write down this, identify the cm star cn part if we want to know the expectation value, right? So this part is easy. Now this part cm star cn, let us try to find out how to write this part. Okay, so we had also learned another operator called as projection operator, which is nothing but equal to the inner product of the two states. Similarly, for I beta was written as beta beta. So these are projection operators. This was discussed in 1 or 2 lectures back, right? So for a general state psi, projection operator can be written as P is equal to psi, ket psi and bra psi, inner product of ket psi and bra psi. Now if we want to write the nth row and mth column matrix element of P, because this is an operator, P is also an operator, so one can write it in matrix form. So nth row and mth column matrix element of P operator, projection operator, can be given as can be written as, you have n p m, right? This is equal to, now put in the value of P as ket psi and bra psi. So what you will get is n ket psi, bra psi and m, right? Okay, now put in the values of psi here. So again, so if I'm writing psi as ket psi, so I will expand it in the coefficients of n. So Cn n summation n, and I have bra n over here. Okay, and similarly, if I'm going to expand this, I will have sigma m Cm star m m, right? So summation will be on this part. So here, so summation will be on this part. Here the summation will be on this part. Okay, now this thing for all other values of n, this integral will go to 0, and only if n is equal to n, this integral will remain. So you are left with this integral will go to 1, and then you are left with Cn over here, and similarly here you are left with Cm star, right? So that means what we have done is we have identified Cn Cm star value, which was appearing in the expectation value of this operator A here. So now we have find out the solution for Cn Cm star as that this is the projection, the matrix element of the projection operator, right? Thus we can now write the expectation value A as summation m summation n. So let me write it completely first. Cn Cm star, and I have m a n. Now in place of Cn Cm star, I will write this. So this becomes summation m summation n So now again you see that this summation m is applied only on this part, right? So what happens? So this identity, this becomes the identity operator, or the unitary operator of order, whatever order this whole eigen system will be, eigenstates will be, number of eigenstates will be, right? Okay, so now basically what I mean is that now the expectation value can be written as summation over n operator p operator a n. So here I have made use of the fact that summation over m is equal to identity, and thus that is basically 1, or unitary operator. So this is 1 and thus can be ignored, right? So now this, what is this term over here now? If you see carefully here, the matrix element of this is nothing but the matrix element. This part is the matrix element of PA matrix, right? And what matrix element? This is just the diagonal element, because the row and the column index are same. So that is this is summation of diagonal elements of PA matrix. Why PA is a matrix? Because P can be written as matrix representation, it's an operator. A can also be written as matrix representation, it's an operator. Product will be a matrix, and for that matrix you can now take the diagonal elements and add them together, which will be this value, expectation value. So this is called as trace. So trace of P and A matrix, PA matrix, right? This is expectation value. So this is a very, very important result. Now this is because it makes your life very simple, that when you have to measure the expectation value of a spin of an operator for a spin, then you take the projection operator, multiply it with the operator which you are using for measurement, and then calculate the trace, and that is the expectation value, right? So the calculation becomes very easy. So now for ensemble of spins, because this is for a single spin case, for ensemble of spins, one has to take an ensemble average So ensemble average is represented as a bar on the top, right? So instead of simply writing as A, so I'm writing as A bar. Now A bar, if I'm writing it as A bar, then my sigma m, sigma n, cm star, cn, this will also be written as bar, and rest was same, m, a, n, right? Now we understood that cn, cm star is nothing but the matrix element of projection operator, nm, p, nm, or in other words you can write as np, bra np get m, right? Okay, so to take an ensemble average, what one has to do is we have to multiply this with the probability density. This is probability density cn, cm star, and d tau, and integrate over all space. Now if you do the same thing here, you multiply this with probability density, what you end up getting is you get the density operator, which is so this is nm matrix element of density operator. And this basically on the left hand side you can write it as cn, cm star, average value as sigma nm, right? So that means now my expectation value using the same set of calculations as done above, what we can write is trace of sigma into a vector. This is a density operator. Okay, this is the matrix element. This is the density operator matrix element. Here this is the complete density operator, okay, or density matrix we can write. So this is now very easy. The calculation is very easy. Suppose if you have Hamiltonian operator, you can take you can multiply density operator or density matrix with the Hamiltonian operator, take a trace, and you have measured the energy, or you have measured the expectation value of the for energy, right? So that's how we have introduced density operator, and we will see later how to use this for various calculations. That is all for today. Thank you.